Hello, George Romanic here. Today's video is devoted to the concept of the Compton generator. What is a Compton generator? It's a simple apparatus that involves only rotating planet Earth and a simple hula hoop. This is an experiment that can be used to demonstrate that the Earth is rotating, or it can be used to calculate the latitude where the experiment is performed, or angular velocity of the Earth. This experiment was proposed by Arthur Compton around 1913, or he performed it around that year, when he was still undergraduate student at his university. Extremely clever man. So, also you might know Compton, not by this experiment, but by Compton scattering if you are studying radiation. But that's not something we are going to talk about today. Today we are going to talk about Coriolis Force, because this experiment related to Compton generator is based on the concept of the Coriolis Force. So, what did Compton propose in about the year 1913? He said, if you have a tube like this, circular tube, filled with water, this one is not, this one is filled with air, but let's assume it's filled with water. He said, if you put it horizontal on a desk, and the water is still, and then you take this tube and you rotate for 180 degrees around the west-east axis, you can demonstrate that the Earth is rotating because there will be induced motion of the water in this tube. Namely, what I just said is, you take this tube, you put it horizontally on a desk. Let's assume this is west-east axis. You take this tube and you rotate for 180 degrees, like so. As a consequence, there will be induced drift velocity of the water in this tube. And that induced velocity is a consequence of the Coriolis effect, or consequence of Earth rotating, being a non-inertial reference frame. Let's now investigate why this would be the case, first qualitatively, and then we will solve the problem on the blackboard. Well, think about it. When this loop is horizontal on this desk, and it's there for a while, let's say water is inside, everything is still, velocity of the water is 0, there is no Coriolis force. But now, when I flip this tube around west-east axis, these particles of water are moving towards the north, and these one are underneath moving towards the south. Look, this one is going towards the north, and this one is coming to the south. Well, there is Coriolis force. So these particles of water over here are deflected to the right as they are moving towards the north, and these that are moving towards the south are also deflected to the right because we are in the northern hemisphere. Coriolis force deflects motion to the right in the northern hemisphere. And these are moving to the right, these are moving to the right in respect to their motion, and there will be induced clockwise circulation in this tube caused by the Coriolis force. As I said, in 1913, Compton proposed this experiment, and he managed to calculate his latitude within 3% accuracy. So today, what we want to do is to repeat his concept mathematically and calculate drift velocity in this ring, in this tube, that is caused by the Coriolis effect. Text of the problem is now on your screens. So, let us first start by sketching this problem and introducing coordinate system. I will have coordinate system where z is height, positive up. x-axis is zonal direction, positive east. And y direction is meridional direction, and it is positive north. So this plane, xy plane, is the plane of this desk. Okay? Let's say that the origin of this coordinate system is O, and this coordinate system is placed in the center of this ring. So this ring goes around, and it is sitting on this desk with O being in the center of the ring. I didn't properly maybe plot this, but you get the point. Now, let us take a point, and I'll call this point, let's say, point A. And that can be this white stripe on this loop. So this point, there is radius vector to this point, and we can already see that OA line is radius vector of this point, or radius vector of this loop. And I will introduce angle theta. Theta is measured from the positive x-axis, namely from the east direction. So we said if this is east direction, then this would be angle theta for this loop. And now what we need to do, we shall rotate this loop around the x-axis, which is west to east. So one more time, what we do is we rotate this for 180 degrees. And this angle of rotation I will call delta. Okay? But now to demonstrate this angle delta, I will provide a separate schematic over here. So let's again introduce this coordinate system z, x, y. This is origin O. Now, what I would like you to imagine, when I start lifting this point A, there will be projection of this point to this plane of the desk. And that plane of the desk is this horizontal plane xy. So now, point is on the plane, but once I start rotating this, point is away from the plane, but there is of course projection of this point on the plane. So I will say, as I start rotating this ring, point A will be somewhere here, let's say. So somewhere here means elevated in the air, but there will be projection of this point, let's call it projection P, on this xy plane. Now we combine these two figures. OA is radius vector r, and this OP I will call projection of this radius vector. So this is projection of radius vector r on the xy plane. This over here is angle delta. Okay? This is the angle for which I rotated this. Namely, now delta is 0. Now I am rotating delta. Delta is increasing. Now delta is 90 degrees. And now delta is 180 degrees when I finish this rotation. Now I can immediately express this angle delta in terms of time. At time t equals 0, delta is 0. I am not rotating anything. Now I will say that at time t equal 1, in 1 unit of time, delta will be pi, which is 180 degrees. So it takes me 1 unit of time to rotate this loop. Well, omega of this loop, omega L, is change in delta over change in time, and that would be change in delta is pi, and change in time is 1, from 0 to 1. So you can see that this angular velocity of the loop needs to be pi to satisfy these time boundary conditions. Or, knowing that delta is equal omega times t, definition of angular velocity, I can see that omega is equal, sorry, delta is equal omega L is pi t. So when t is equal 0, delta is equal 0. When t is equal 1, delta is equal pi. So now what I did, instead of dealing with this angle delta, I can use pi t and deal with time. And that's more convenient, we will see later when we start doing differentiation. You can keep delta without this time, but I think this is more intuitive, and you will see that later in this video. Okay, so we covered this part. Now, what we need to, so what we know, let's just recap. What we claim that we know is this angle theta, this angle delta that is expressed as a function of time, and we know radius of this loop. So we need to find coordinates of this point A as it is rotating as a function of r, theta, and delta, or consequently time. So that's what we will do here on this part of the blackboard. To do that, we will use a little bit of geometry. I will call this point here on the x-axis capital X. And I will project this point P on the y-axis, and I will call this point capital Y. So I hope you can see from this figure that this line YP is actually x component of this point A, and this is positive. So this length is the x component of point A. This length, x p, is clearly y component of this point A, and notice that in this case it is negative. It is negative because origin of my coordinate system is over here. And lastly, this PA is the z component of this point A, and in this case it is positive. Okay? So what I need to find x, y, and z, I need to find these distances. Well, let's first investigate this triangle over here, XPA. So let me plot that maybe like this. So if I have here x, here I have P, P, and then I messed up. This should be then X, this should be P, or I need to reverse this triangle. Let me better reverse letters. It's easier. So I hope you see what I want to say. So if I go from X point, I go from X point to P point. Then from P, I have to go vertically following the Z coordinate to point A over here. Now, this is 90-degree angle. And XP, XA is actually angle delta. This is angle delta, as you can see from here. Now, XP is Y, component of this point A. So a little bit of trigonometry tells me that Z, this line, is equal this XA, this times sine of angle delta. Or that is equal XA, this is capital X point, sine delta is pi times t. I can also see that tangent of this angle delta is opposite Z over Y, but Y is negative. Keep in mind that Y is negative. Which means that Y from here is equal negative Z over tangent delta, but delta is pi t. So this tells me if I find Z, then I can plug it in this equation and find Y. But to find Z, I need this distance XA, which I don't know. So I need to find this distance XA from an independent triangle from that figure over there, and then combine with this equation. So to do that, we will identify another triangle in this figure that has this distance XA, but it's not that triangle over there. So if you maybe pause the video for 2-3 seconds, as Agadmatur would say, can you find a triangle that contains XA, but it's not that triangle over there? Well, I claim that this triangle, OXA, contains this this XA line. So let's see how we do that. So we go from O, from point O, we go to point X. And then I go normal to point A. And I go back to O. And notice that OA is R, radius vector of this circle, which is known. Okay? Now, you also have to know that this angle between east axis, x-axis namely, and OA is theta. So this angle over here is theta, which means this angle over here is theta. OX OX is the same as YP, and YP is the X component of the A point, and okay, so from here, what can we conclude? We can conclude that this XA is equal R sine theta. Now I take this and I plug it over here, and I will get that this is equal R sine theta sine pi t. And this is Z component of my rotating ring. Before we get Y component, let's just re-establish what we did. So what I said is there is this loop, take this point, as I'm rotating this point for 180 degrees, what we just derived over there is the height of this point in respect to the table as the loop is rotated for 180 degrees. So that's the Z component. What is the Y component? Well, we calculated from here. So that will be equal negative Z is this R sine theta sine pi t divided by tangent pi t, and that would be cosine pi t times sine pi t. So this sine and this sine cancels, and that means that Y is equal minus R sine theta cosine pi t. This is Y component of the point A, this white stripe that is rotating. And X, we can see simply from this figure that the X component would be R cosine theta. Okay? And logically, notice something. If you are imagining this, X-axis is measured along this edge. As I am rotating this point, the X component doesn't depend on time because I am not moving this point left, right. I am just changing height and I'm changing height and the Y component of this point. I am not changing X component with time. X component only depends on theta, and that means if I pick different, not this white stripe, I pick point over here, then of course it will have different X component. I hope this is clear. Now, when we know these coordinates of the rotating point, we can use that and combine it with the expressions for the Coriolis force to find drift velocity of the water. Because as this point is moving, and that point means parcel of water has these coordinates, parcel of water is moving, Coriolis force will act upon it, and therefore we need to combine this with the expressions for the Coriolis force. Let me first erase the blackboard. Okay, so what we derived in the previous segment of the video is that the components of the point A are these, x, y, and z, as we are flipping this loop. Now, we combine this with the Coriolis force. Now, Coriolis acceleration in the A Coriolis in the x direction, and x is zonal direction, positive eastward, is equal, so that would be 2 omega of the Earth, 2 omega of the Earth times sine phi, phi is latitude where I'm standing, times v, and v is the v component of the parcel of water, meridional component of the parcel of water that is being flipped, minus 2 omega of the Earth cosine phi times w, where w is vertical velocity of this parcel of air, water that is being flipped. Coriolis acceleration in the y direction is equal to omega e sine phi times u, but with the minus sign in front of it. And the Coriolis acceleration in the z direction is equal to omega e cosine phi times u. So keep in mind that this u, v, and w are not in the cosine and sine terms, but multiplying this whole term. Okay? Now you might say, but how do I know this? Well, you have to know something. And in order to know Coriolis acceleration components, you can watch my previous videos. I derived these components at least 4 to 5 times before. So I just know them already. Now, this is a very important part of the video because we are introducing some assumptions. Well, first assumption is that, which is extremely reasonable. Again, if this is my parcel of water, as I am rotating this parcel of water, it will only have v and w velocities. W vertical, so if it is here and I start rotating it, look, I'm increasing height, that means w exists, and v of course exists because this that is now on the south side gets on the north side, but during this rotation around the angle delta, the u component of the velocity is negligible. Well, if that is the case, then this one is approximately 0 and this one is approximately 0, and that means if we take this for granted, then this is really 0, not approximately. So these disappear, which means that only Coriolis acceleration in the x direction survives this rotation. But notice that this term over here also goes to 0. Now, you might say, but why would that term go to 0? The reason is, as I am rotating this for 180 degrees, this white point first goes, in the first 90 degrees, it goes up. W is positive. In the second 90 degrees, it goes down. W is negative. So this contribution to up and this contribution to down cancel out. And they cancel out, which means this term over here associated with W cancels out. Formal way, this is physical reasoning. Formal way to demonstrate this is to have this term, but then when you combine it with here with this expression, because W is dz dt, when you combine with this expression and integrate with respect to time, that integral will be 0. And you can convince that yourself. I'm not going to do it here in order not to make this video too long. And it's already long. Now, that being said, we concluded from this reasoning that Coriolis acceleration only exists in the x direction, and it is equal to omega of the planet Earth sine phi times v. Now, what is v? V is dy dt. That is why we had to find these coordinates. And you can see now, it turns out we only need really y coordinate, because these will not play the role in our derivation because of the physical reasoning that I just talked about. But we have all coordinates for you to admire over here. So what is dy dt? Dy dt is equal, so this is differentiation with respect to time. Derivative of cosine is negative sine, which means it will cancel with this negative, and I will have here, and this pi will go in front, so I will have here pi r sine theta sine pi t. So this is v component of the velocity of this white stripe. And I told you, when we start differentiating, it is convenient to express this angle delta through time, and now you see why, because now I'm just differentiating with respect to time, and it's simple differentiation. Okay, now when I plug in this expression over here, we get that A Coriolis in the x direction is equal 2 pi r omega of the Earth sine of the latitude sine of the angle theta around the ring and sine of the rotational angle delta, namely pi t. So this expression over here is the Coriolis acceleration that this parcel of water experiences as we are rotating this loop, okay? But this is not the end of the problem, because this problem, as you can see, is very sophisticated.
I mean, I know you're a sophisticated guy.
The video
is a mess.
What is driving this motion of water is not entirely Coriolis acceleration in the x direction, but component of this acceleration in the circumferential direction, component along the ring. Let me sketch this over here maybe. So what I'm saying is, if we have let me see. This is our ring. Here is origin O. Here is point A. Here is radius R. This is now a ring that is in the phase of rotation. What we just calculated is that there is this Coriolis acceleration, A Coriolis, in the x direction, because this is the x direction positive to the east. And let me just think. So if I am moving this from south to north, then the Coriolis force acts to the right, and to the right is towards the east, so that's correct over there. As I'm moving this towards the north, so this is in the flipping stage, Coriolis acceleration is to the right, and that's to the east. But you will agree with me that this is the component that is driving the water to go around. So we can say that there is acceleration in the theta direction, azimuthal acceleration from this x component, and there is this normal component which doesn't contribute to water going around. So let's call this AR, radial component and azimuthal component. From this, I need azimuthal component because that is the one that is driving water to go around. Well, this over here is angle theta. And now you have to recognize that this is the same. These are parallel lines. These are parallel lines, which means this over here is also angle theta. And that means from this figure that A theta is really equal A Coriolis x times sine of angle theta. So this is the contribution of the x component of the Coriolis acceleration that drives the water. That means that A theta is equal, I multiply this equation with sine theta, and that is 2 pi r omega of the earth sine of the latitude sine squared of theta times sine pi t. A lot of sines, and this is a sign that we got a correct solution for the acceleration that is driving the water to go in circle. Now, I didn't mention, but why would we use water? Why not using air that is already inside? Well, water is incompressible fluid. And that means if one parcel of water starts moving, all parcels have to have the same drift velocity. For the air that is compressible, that doesn't have to be the case. So that's why I'm saying we can have water or some other liquid inside. Okay, but now you further have to realize that this is acceleration in the azimuthal direction of this point A. But we need average acceleration for all points around this loop, which means we have to integrate from 0 to 2 pi to cover all points on this loop that is rotating. Okay? Now, what is the averaging of some function? Let's talk a little bit about mathematics. So, if I have function f of x, what is the average of this function on some interval a to b? Okay? So this is how the function looks like. And let's say this is a, this is b. What is the average of this function between a and b? Well, we usually say f over bar, that's average. By definition, that is 1 divided by b minus a integral from a to b f of x dx. This is averaging operator. Again, you just have to know this from mathematics, but if you don't know it, now you know it. So, to find average azimuthal acceleration, a theta average, I need to integrate with respect to theta. So it will be 2 pi r omega of the planet Earth sine phi sine pi t sine square theta d theta integral from 0 to 2 pi, and now I have 2 pi minus 0, so I have to divide this with 2 pi minus 0, which is just 2 pi. So this is the averaging operation. Now notice that this 2 pi and this 2 pi conveniently cancel. And in a separate video, I didn't want to do it in this video, this would be too long video, I will demonstrate in separate video, I will solve this integral, which is not so difficult to solve, that this integral is equal pi. So integral sine square theta d theta in the limits between 0 and 2 pi is equal to pi. Check my associated video with this lecture and you will see how I get that. So we get that a theta average is equal pi times r theta earth sine phi sine pi t. Beautiful result. Again, let's go back to our concept. What did we do here? Well, what is this? This is azimuthal acceleration caused by the Coriolis force for this point A. But we will have different values for different points, so we average around the loop. Averaging is given by that function over there, which means that this result is average acceleration of water in this loop as we are rotating it. Okay? Well, as we are rotating it means that we also need to integrate this with respect to time, because this is expression at a given moment in time, so I need to carry out one more integration, and that's integration with respect to time, and that's the time of flipping this hula hop. And I will do that after I erase this blackboard. So what we concluded with in the previous segment of this video is this expression over here, which was the average azimuthal acceleration of water in this loop. But we are not interested in acceleration, we are interested in the drift velocity. And drift velocity is the integration of this with respect to time. Namely, I can say that average, v theta average is d v drift dt. Okay? Where vd is drift velocity of these, which means dv drift is equal a theta average dt. So plugging in the above expression over here and integrating left time from 0 to vd, I will get that drift velocity is equal r pi omega e sine phi, which is latitude, sine pi t integral dt. And now what are the limits of this integration? Well, you know that they are from 0 to 1, because we defined angle of rotation at the beginning of the video. Let me refresh your memory, that was very long time ago. We said that this angle delta, angle of rotation of this loop, is pi times t. And when t is equal 0, this angle delta is 0. When t is equal 1 unit of time, we flipped this for 180 degrees. So 180 degrees corresponds to t equal 1, and that's why limits are from 0 to 1. So now I decided to solve this simple integral in this video for you, because it's very simple, and I'm sure many of you perhaps even know already what the integral of sine pi t dt with these limits is. But for those of you that don't panic, we'll do it here. So let's call this integral S. Integral here. So S is equal integral 0 to 1 sine pi t dt. How does one solve this integral? Very simple. You can introduce a substitution k that is pi times t. Therefore, dk is equal pi dt. Now, plugging that in our integral S, we get integral sine pi t is k. dt will be dk over pi. And what are the new limits? Well, the new limits, when t is 0, k is 0. When t is 1, k is pi. And this is equal integral of sine is negative cosine, so this will be negative 1 over pi, this pi, cosine k in the limits between 0 and pi. Well, that is further equal negative 1 over pi cosine pi minus cosine of 0, and that is further equal cosine of pi. I hope you know it's negative 1, so this is negative 1 over pi minus 1 minus cosine of 0 is 1. So minus 1 and minus 1 is minus 2, and this minus over here results that this integral is 2 over pi. Okay? So that's the integral S, which means that Vd is equal r pi omega e sine phi, and the integral S is 2 over pi, so pi and pi cancels, and we get that Vd is equal 2r omega e sine phi. So, what is this solution? This is the drift velocity in this loop filled with water when I flip it for 180 degrees, and this drift velocity is caused by the Coriolis effect. Let me give you a few additional information which are very, very interesting, indeed very interesting. If you decide, oh, first of all, this r is radius of this ring. Omega e is angular velocity of the Earth, approximately 7.3 times 10 to power negative 5 hertz, and phi is latitude. Now, if you decide to conduct this experiment in a way that you start when the loop is vertical, like this, okay? And now you flip it 180 degrees. So you go from vertical to vertical. You can do that, but the result that you will get is that drift velocity is 2r omega e cosine of this angle phi. Instead of latitude phi, instead of sine, you will have cosine. You can convince yourself by repeating this derivation, but starting from vertical and going back to vertical. In fact, when Compton performed this experiment and he had nice apparatus where he had a microscope, he was looking into the liquid, and the liquid was, I forgot, was it water with some particles of coal, oil, or something like that. He was able to determine the latitude of his position within 3% accuracy. So you can see Compton, of course, he knew the radius of the ring, r. He found drift velocity by measurements, put microscope, very nice measurements. Omega e, angular velocity of the Earth, is known, so he was able to calculate phi. And I believe he used actually apparatus that was vertical, flipping to vertical. Of course, if you know latitude and you measure Vd, you can calculate angular velocity of the Earth. So in this respect, Compton's generator, Compton experiment, is even more powerful than the Foucault pendulum, because in the case of Foucault pendulum, you cannot calculate all these parameters knowing the other parameters. What else should I say at the end of this video? It's already very long. Of course, there are many assumptions that entered into this derivation. One assumption is that there is no friction. Of course, when the water starts moving around, there is friction with the wall of the tube, and we didn't consider that. So if you are to perform this experiment, what you want is to measure velocity in the center line of the tube, because then you are the furthest distance from the wall. Lastly, if you take latitude to be 45 degrees north, which is where I am, 45.5, that's Montreal, McGill University, and you take a ring which has radius 1 meter, which is larger than this, then I believe you can plug in and of course omega e is approximately 7.3 times 10 to power negative 5 second minus 1. Then if you plug in these over here, you would get that the drift velocity is approximately 0.1 millimeters per second. Of course, very, very, very weak, small velocity, but what did you expect? Because motion is just 2 meters given this radius, and therefore Coriolis effect is very minor, and therefore drift velocity is very small. But this is not that small that you cannot measure it with sufficient microscope and apparatus. I cannot do that experiment with this loop, but if you stay tuned, I will try to do a similar experiment relatively soon to demonstrate this concept, not just qualitatively, but we get experiment that gives us some numbers. If you are following me, and you are also following these big channels, Veritasium and so on, you can comment on his video, because they have a lot of money, and you can ask them to perform this experiment. So what Veritasium and these other guys could do, they could make a hula hoop 10-meter radius. Radius 10 meters. If the radius is 10 meters, look, then drift velocity becomes much larger. So if you set up apparatus where you rotate a hula hoop 10-meter radius, then drift velocity will be such that you can even observe it with your eyes. I don't have resources to do that here, but maybe these big YouTube channels can do it, so go there and brag about it. If you watched the entire video, I thank you very much, and until next video, goodbye.